Good afternoon. This is Schweitzer. We're going to do a little bit of application of we call angular. I'm going to call it angular overtake. I'm not sure if that's a term that's used widely, um, but it's a term we use here in our school. Um, so essentially, we have here is big balls rolled down a hill, right? So it's the same hill, and this ball's rolled. Shears let go, and it gets a certain way down. It rolls, 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 and it rolls for 5 seconds. So it's a little ways down the hill, and then another smaller ball starts up rolling next, the same path, and eventually it's going to pass that ball because it's accelerating at a greater rate, and it also has an initial rate. It'll pass it, okay? And we did a linear overtake situation where we had um, x initial plus vit plus 1/2 at squared equals the location, and then equals xi plus vit plus 1/2 at squared. And then, at that point, this would be ball A, this would be ball B, and we would solve for the time it took to get to the same spot. And eventually, we could do that. We did that already. Here we're going to look at rotation. So when would this ball here is rotating, because it's got a larger radius, um, it goes through a different number of revolutions than the small ball as it rolls over the same distance, okay, at the same time. So let's look at it in terms of that because we have the same exact formula. So ball A has a certain um, angular rotation initially, and then so the number of radians has gone through at a certain time, plus the angular velocity times time, plus 1/2 angular acceleration times time squared equals a total number of rotations at a certain time, equals for ball B the total number of rotations, amount of rotation at that time point initially, or at some time, and then plus angular velocity times time, plus 1/2 angular acceleration times time. So we're looking at this 5 seconds in. 5 seconds in. So that is where really where it says initial is really 5 seconds. That should be a 5 here, and this should be a 5 here. Remember, that 5 is just a little subscript, meaning that what's the rotation at 5 seconds? Okay, so we're looking for what time. So I want time here, but I have to figure a couple things out here first. So let's plug in what we got. This guy here, the B, is going to be a little more straightforward because it's just starting. I got to do two parts here. I want to know what are the conditions when we're starting, and what are the conditions 5 seconds later. Okay, I shouldn't say that. I want to know the conditions at 5 seconds later, at 5 seconds, and then I want to know the conditions when what happens when they actually go through the same number of rotations. So what's happening at 5 seconds? And that would be easy for B because we're given that immediately. First of all, B has not, I'm going to take this out here for a moment. B has not gone through any rotations yet. It's just starting. Its initial angular velocity is 2, I believe, 2 radians per second times some amount of time, plus 1/2 angular acceleration, which is 0.75, and then I have time squared. All right, now where we're going to get into a little bit of a difference here is where A has gone through some rotation, so we got to figure out where is A located. Now A still has the 1/2 0.5 t squared. This is unchanged, but its angular velocity started at 0, but now it's gained something here. Okay. So we want the velocity at that 5 seconds. Okay. So let's take a moment and let's figure that out. I'm going to jump to the next page here. Let's just figure out this guy's initial materials here. So we have a wheel that's spinning for 5 seconds. This is great review of just a lot of our stuff. Seconds. It's got a radius of 5 meters. Okay, so that's a big wheel. 5 meters, whatever, it's number. And we have two formulas. We have angular velocity equals angular velocity initial plus angular velocity times time plus 1/2 angular acceleration times time. And we have angular velocity at some time equals angular velocity initial plus angular acceleration times time. And we want to do 5 seconds. This is going to tell me where I'm at with ball A in 5 seconds. So let's run this thing through. So initially, let's do this one here first. So initial angular velocity is 0. It doesn't have any push. And the angular acceleration is 0.5. We're doing this for 5 seconds. So 5 times 5 is 25. So this is going to be 2.5 radians per second. That would be my angular velocity at 5 seconds. Okay. All right. Now the next thing we want to do. So the next thing we want to do is find out, okay, how much actual angular displacement do I have at that 5 seconds? It's gone through some rotations. It's getting a head start. So in this point here, okay, we got this guy here. Remember, this angle is the total amount of rotation that we've gone through. So it starts at 0 and it runs at 5 seconds. Initially, it actually is 0 too. It didn't get a push. This is initial. This is at time 0. Okay. Um, so it's got an initial. The time is 5 seconds. That's out. Plus so that remember, this is we're trying to figure out what happened to A before B is even rolled, right? So now this guy is going to be 0.5 square in there, and then 5 squared. So this is going to tell me how much rotations I've gone through before I even go. All right, there you go. So in this point, let's do that math. Notice I don't even need the length of it. So 5 squared times 0.5 times 0.5 equals 6.25 radians. Okay, so it starts slow, and total amount of actual rotation is 6.25 radians. Now keep in mind that a circle is about 6.2 rotations. Okay, so that the radians is about what's almost just rolled one time around. That's about it. Now it's got a big radius, so it's traveled a long ways. You could actually figure out how far down the hill right now that this ball would be based on its rotation. So it'd be the circumference or the distance traveled is equal to the angle of rotation of radians times r. So now you could put the 6.25 in there, and you could put times r, which is 5 meters, and you could actually find out how far down the hill this guy now is before he even gets started, before B even gets started. But that's not really what our concern is here. Our concern is, okay, let's get back to our original problem. Now we know where this thing is located. It is now traveling. I'm going to move over this little circle here so I have room. Okay, so now if you aren't following me yet, you should start to get a little more clear. This thing has traveled, is now rotated 6.25 times. It has an initial, at 5 seconds, its velocity has, its angular velocity has creeped up to, well, 2.5 would be that guy, okay, radians per second. So that's 2.5. Now it's going to continue to get bigger because of the acceleration. 2.5 and then t. Okay. All right. This is it. This is all we got. So I want to know what time these two things have the same amount of rotation. It might be very quick. that little ball, it's going to rotate. Um, well, I mean, it's going to rotate a little bit faster. Okay, so let's do this. So this is, and I don't even know if we'll give you the actual answer here because it's just a math problem at this point. Maybe we'll just talk about how you do the math problem, and we'll get it set up for you, and then you can run it yourself. So because we have a variable that's t, and we have a variable that's t squared, we got to get everything kind of combined here. So I'm going to move all this stuff because this is a quadratic. Okay? No two ways about that. We're going to do a quadratic here, so I'm going to move everything over. So 6.25 is my only non-variable factor. Subtract over the 2, so minus 2 is going to be 0.5t. And then plus, okay, now this guy here is going to be half of that, so 0.25 t squared. And then this one, half of that, half of 0.75. 0.75 divided by 2 is 0.375. All right, so minus 0.375, and that's just going to be subtraction here. So 0.25 minus is pretty easy math here. 0.125. So this is going to be a negative 0.125, okay, t squared. And then at this point, we're just going to plug it into our quadratic formula. And of course, remember that this is your A component, this is your B component, and this is your C component. So grab your quad. A is negative 0.125. B is, so it's just going to be 0.5. And then the C is 6.25. And we're getting about 9 seconds. If that worked out right, you can check my math on that. If I'm wrong, I apologize, but that's 9.3 seconds. Now that doesn't mean they're in the same location, okay? And you could actually take and figure out how far down the way they would be when that happens, but they're definitely not in the same location because every time this guy makes a rotation, we could even figure out where this guy is at this point, okay? Based on its, its tangential velocity, but because it's not every time it makes a rotation, it only travels, a much shorter distance. This guy makes a rotation, travels much farther. All right. Again, thank you very much.